Hello, just a quick video here, John Golden, to do a little bit of implicit differentiation. So we have adjustable curve. I've made a GeoGebra sketch where you can change exponents or change coefficients. And I want to see if we can do the uh, implicit differentiation kind of for this general one, so we can see how it works for this whole family of curves. So you'll forgive my poor writing on this tablet. I'm by no means the expert that my kids are when they're working on this. Okay, so we treat this just like a derivative. Like if we were doing the regular derivative of a as a constant times x cubed, we'd just say 3ax squared. If we were doing chain rule or related rates, we'd say 3ax squared dx dt if we were thinking about x as a function of something else. In this case, we're going to use those differentials. So we're going to say, take the derivative. So we'll say 3ax squared. And then we're going to keep track of the change in x using the differential. So a little dx. Okay. Then what we have here is a product. It's x and the y. So we're going to apply the product rule. So it'll be b, the derivative of x is 1 times y. We're going to keep track of that derivative of x. And then we've got the other term, which is going to be bx times derivative of y, which is 1 dy. And then this last term is going to be 2cy with the dy. And it's equal to the derivative of 1, which in our case here is 0. So we're going to factor our two different kinds of derivatives. So we've got those derivatives where we're taking the derivative of x, and we've got the terms where we were taking the derivative of y. Now we're never going to have a term where we've got the dx and dy, because in each bit we're only taking the derivative of one variable. Okay, that's equal to 0. So we could say that this y stuff is equal to the opposite of the x stuff. If we divide both sides by x, dx, we'll get the kind of derivative we're looking for. But we've still got all this other stuff over here. But we can divide both sides by that to get the derivative by itself. So a bit of your algebra skills. Now this is something we haven't seen anything like. We're saying it's a derivative, but the x's and y's are mixed together. And the crazy thing is, in this world of implicit curves, maybe we're interested in dy dx, maybe we're interested in dx dy. We're thinking about the variables used together instead of what we've gotten used to, which is x as an input, y as an output. But here we have our derivative. That's to evaluate at a point, we have to know an x and a y that are on the curve. Right? So it's not, we can't just plug in an x value and see what the value is. So we have to know a point that's on the curve, the x and the y, and then we plug in the x and y values, and that can give us the slope at a point. So for example, here in the picture, we've got a point on the curve, 1.71, 1 and 71 hundredths, 2 and 9 tenths. We plug those in here with the a, b, and c values that we've selected. That would tell us that the slope of a tangent line to the implicit curve at this point has slope 6/10. Okay, so in some ways it's the exact same as what we've done, and in other ways we've got this new idea of keeping track of the differentials. All right, hope that's a good start for you for thinking about differentiation in the context of implicit curves.